Hi, welcome back. This is the Tutor Wizard. Please subscribe right here. You'll get notifications for this series and many other ones on my channel. Basically, what we're doing today is this will be the start of this series for multivariable calculus course. What we're going to do today is introduce basically a quick overlay of what we're going to do in the course, and then start with one of the first basic topics in the first chapter that we're going to discuss. What is multivariable calculus? We're going to do clever, have to draw a fancy picture, so I pre-drew one already today. But essentially what we're going to do is we're going to discuss chapter 1 is called partial derivatives. Essentially, we're going to look at functions of multivariables and then do analogs of what we did in calculus for one variables and look at limits and continuity and derivatives and all of those types of things, tangent planes and tangent lines now in 2 and 3 dimensions and then possibly higher dimensions, but we're going to focus primarily on doing this for functions of 2 variables and 3 variables, or multivariable calculus. All right, let's do this. Okay, chapter 1, partial derivatives. What we're going to do in chapter 1 is essentially work towards what we're going to call partial derivatives, or what does it mean to look at the rate of change of a function when we have more than one variable. And so we're going to look at the rate of change in different directions or in the direction of each variable, and then talk about different scenarios. First of all, what we're going to discuss is we're going to focus primarily on functions of 2 variables, x and y now. Instead of y depending on x, we're going to have z depend on x and y, and then we'll move it up to 3 dimensions and then higher than that if we need, depending on what questions we're doing. First, we're going to give a definition of what do we mean by a function of more than one variable. We'll give the definition explicitly for 2 variables. Definition: let D be a subset of R2. So again, I'm using notation, but this is R2, the space of all 2-dimensional vectors. D is a subset of that, so this is how I write this. D is a subset of R2. Be a set. What we're going to do is a function f from D to R is a rule that assigns to every point xy now in D a unique value z equals f of xy, which is now in R. So this is to mean in. So the definition is completely analogous to the one-dimensional version. In one dimension you have let D be a subset of R, then a function is a rule which assigns to every point x in a domain, we're going to call it, a unique value y equals f of x. This time we're taking a subset D of R2, and now we have a rule which assigns to every ordered pair xy in D a unique value z equals f of xy, which is just a real number. Pictorially, we can view f like this. We take the region D now, we can still draw this. Once we get in higher dimensions, this becomes extremely hard to draw and we can't. But for specifically functions of 2 variables, we're still going to be able to draw these scenarios, and we'll have the graph, and the graph that'll be coming next, but the graph will be a surface instead of a curve in the plane. We'll have a surface in 3 space. This is the domain D. We take every point in here and we assign it to, remember, even though this has the big machinery z equals f of xy, this is a point on the real number line, and this is a good way to pictorially write f. And the other way we're going to write this is f is going from, sorry, not always R2, from D to R, where D is, remember, always a subset of R2 or Rn, depending on what dimension we're in. Okay, to recap one more time, if we have f is a function now of 2 variables, x and y, coming from D and mapping to R, we call D the domain of that function, f of xy, and the range of f is all values f is able to obtain, i.e. the range of f is z in R such that there is a point x, y, and d with z equals f of x, y. Let's do a couple examples. Example 1, z is f of x, y, which is the square root of y minus x squared. So it's a function of the two variables x and y, and it maps to a real number. And it's asking us to find the domain and range of f. Solution. 1, for the domain. The rules still apply when we're doing functions of more than one variable. Essentially, we have two main mantras, and then possibly if we have logarithms and exponentials, we have to have a third mantra. But mantra 1 is you can't have negatives under even nth roots. So 2, 4, 6, these even nth roots, we can't have negatives under them. That gives us an inequality that we're going to use right away. Mantra 2 is you can't divide by 0. We don't have any fractional expressions in ours, but you're looking for that, and then you don't want the denominator to be 0. That's how we eliminate points. And you can't have negatives in logarithms or 0. So you have to have strictly positive values in logarithms, which we don't have in ours also. I do have a square root, which is even. The square root of y minus x squared, that immediately tells me whatever's inside there has to be positive or non-negative. What does that give me? If you want to intuitively look at what that says now, this is saying that our domain is what? If I look at y equals x squared, when that equals this is if and only if, remember, y is greater than or equal to x squared. When y equals x squared, you're hopefully familiar that this is the parabola from calculus of one variable. So this is the graph of that as a curve, which we're going to get, which is the u. And now we're saying we need, in that plane R2, we need all points x, y, such that y is strictly larger than x squared. So that's going to be, this is the domain D that we're looking for. Good. For the range, 2, the range, what we notice is we do this the same as we would for a function of one variable. Also, I look at z. Z is equal to the square root of y minus x squared, which is greater than or equal to 0 always. So the range of f is z in R such that z is greater than or equal to 0. This is our range. Let's do one more. Okay, again, we're given another function. Z is 1 over xy now, and we want the domain and range. From this, what do we see? Essentially, we're going to have to do cases for the range, but first of all, let's do the domain again. The domain, what do we need? The domain says that we're going to have, I need x, y cannot equal 0. That says either x is not 0 or y is not 0 or both. X and y are not 0. What does that do for me? The domain is going to be now what? We have to just eliminate those guys, and I guess we could get it in a different color even to emphasize. This will be the domain. Everything except for the x and y axis is the domain of this function. This is D. For the range, we want to do cases. 1, x and y are both greater than 0. This says z is strictly greater than 0. If 2, x and y are both less than 0, then their negatives will create a positive, and that will say z is greater than 0. Either way. In the third case, if x is positive and y is negative, this says z, which will be the product, 1 over the product, will be negative, strictly less than 0. And in the last case, 4, if x is less than 0 and y is greater than 0, this says when I multiply them and do 1 over, this will keep z less than 0 still. So either way, z is strictly larger than 0 or z is strictly less than 0. So z is never 0. That tells me my range is equal to negative infinity, 0, union, 0, infinity. This is the domain and range of this function. Good. Okay, next time what we're going to look at is the graph of a function of two variables, x and y, and then we're going to look at level curves and level surfaces. We'll start dealing with slightly with functions of more than two variables, three variables, but specifically we're going to focus on the graph of functions of two variables. Please subscribe here. You'll get notifications for this series and many others on my channel. I'll see you next time.